Hello, everyone. My name is Jason Ikonis. I'm an application scientist here at IonQ, and I'm going to talk about the first of the three challenges that we are going to present this year. This challenge is on what's called quantum state tomography. So in general, when we design quantum algorithms, there's two portions to this algorithm. We have a quantum circuit, which executes the algorithm, and then we have a series of measurements which extracts information from the quantum state that we prepared. And usually we design algorithms so that we could efficiently extract information with a few measurements. And we don't need to actually know what the full quantum state is at the end of the algorithm. However, in some cases, you actually want to know the entire quantum state that you prepared with your quantum circuit. And in order to redesign that state, you need to perform a larger number of measurements on your state. Figuring out what the full quantum state is what's known as quantum state tomography. In general, this is actually very hard to do. If you have a general quantum circuit, reconstructing the exact wave function that you prepared just from your measurements will usually take an exponential number of measurements. But there's some cases where you could actually efficiently reconstruct this wave function with just a finite number of measurements. And so we're going to dig into this with this challenge. When I say a measurement, what I mean is you prepare your quantum state and then you perform one measurement shot. It gives you a single bit string out. You perform a whole series of these shots and you get a sequence of bit strings. So that gives you measurements in what we call the Z basis or the computational basis. To reconstruct the actual wave function, you need to measure in multiple different bases in order to get not only the amplitudes of the quantum state, but also the phase information. The way that we measure in different bases in quantum computing is that we apply an extra circuit at the end of our circuit that prepared the state, which will rotate into a different basis. And then we again measure in the computational basis and get a series of bit strings. And so by taking a series of shots from circuits that are measured in different bases, we could actually reconstruct the entire wave function. And when I say reconstruct the wave function, I mean this. Our quantum circuit or quantum state was prepared with a circuit which we'll call U hidden, which we don't know anything about. We want to find a new quantum circuit, which I call U-gen for U-generated, so that when we apply the inverse of that circuit, we get back to our initial starting state. So that basically this overlap is equal to 1, or that U-hidden plus the circuit for U-gen inverse gives you the all-zero state. Okay, so let's get on to the challenge. So there's a couple different ways, or couple different types of problems, as I mentioned, where you could efficiently do this quantum state tomography. The first type of problem, the first type of quantum circuit where this is possible is when you don't have too many qubits. You only have a few qubits and you want to do not too many measurements and reconstruct the full state. So as our first warm-up problem, we're going to start with a quantum state on just a single qubit. So this is just a 0 state plus a 1 state with 3 hidden parameters, A and B, which you consider to be the amplitudes, and they could both be positive real numbers, and then this complex phase, e to the I theta. And our goal is by taking this unknown state with A, B, and theta, measuring this state in different bases, and figuring out what A, B, and theta are. So for this challenge, you're going to think that you have a finite number of shots, which I'm going to stick to 100. So each measurement basis, you have 100 shots. And then you could measure in up to 20 different bases, which means you could apply a quantum circuit at the end of your state, which rotates into a different basis with 20 different circuits, and each one gets 100 shots. And so from those measurements, you should be able to figure out what these coefficients A, B, and theta are. In fact, for this problem, you won't need 20 different bases. You could do it with just a few different bases. So this part 1 here is going to be the first star that you get for this problem. And this problem really is to walk you through the process of this problem and how we're going to approach it. So in part A, you're just going to explain how you could actually figure out just from a sequence of measurements in different bases what these parameters A, B, and theta are. So this is just in words, and I gave you some hints about how you could actually measure in these bases. In part B, to get the full star here, you're going to write a program in Qiskit, which takes an unknown state on 1 qubit, performs these measurements, reconstructs this state, meaning you get U-gen hidden. And they give you some little pieces of code here to help you along. So first of all, this first chunk of code is just going to create a random initial state. So this is just for demonstration purposes. Once you get this hidden state, you should pretend you don't know what this quantum circuit that you actually use to create the hidden state is. You just have some circuit U hidden that creates a wave function. After that, you're going to measure in different bases. So I gave you again a little code snippet for how to do this. But basically, you have your circuit that created the state. You're going to append some number of gates at the end of that circuit, which you're going to add here, figuring out what those gates are. Find the full circuit composed of these two components, and then measure with 100 shots. And you could do that, multiple times to figure out what these coefficients are. And then to find your final score here, using those measurements, you're going to create a circuit which creates the hidden state, and then put it into this function here, which takes the hidden state plus your circuit and gives you out a score. The closer your score is to 1, the better you are. And so for this problem, you should aim to achieve a score better than 95%. So that's kind of the warm-up problem. The second problem increases the complexity, not too much, but this will be your second star. We're going to now have a hidden 2-qubit quantum state, and your goal is to figure out what these complex coefficients A, B, C, and D are. So first, just explain how you would do this, imagining that A, B, C, and D are real numbers that could be either positive or negative. And then in part B, then imagine that they're actually fully complex numbers. And remember that you could only reconstruct the state up into a global phase. So you could basically consider A to be a positive real number, but then B, C, and D are complex numbers. And then in part C, you're going to perform the same procedure as in part 1, where you write a program that will actually take a quantum state, which you could again generate using this code snippet on 2 qubits this time, and reconstruct it using the same get score functions from part 1. And then part 3 is just describe, no need to code up a solution here, how you would extend this protocol to do even more qubits. You're going to need to measure in more bases in this case and take more shots, but just describe how you would extend it and how many different measurements you would need to apply. Problem 2 is actually giving you your third star, and we're upping the complexity quite a bit here. This is a class of quantum states that have a specific property. They're called graph states. They're generated only using Clifford gates. You should look into the properties of these graph states, but basically, with these graph states, you can figure out what this quantum state is, and you could design the circuit U-gen, which inverts this quantum state preparation, for quantum states that are made on, many qubits. And you could do this still using just 100 shots each and less than 20 measurement bases. And so this problem is going to walk you through how you could actually do this tomography when you have these graph states. So again, in part A, you should look specifically into the properties of stabilizers. What are stabilizer operators, and how do they help you design how you could actually invert this quantum state? And then generating these Clifford states, again, you could have a random graph state. With this code here, we'll generate a random graph state. Again, perform this tomography on this state. And then finally, in problem 3, this is the hardest problem of the 3. Basically, the third class of state that you could again measure using an efficient number of different measurement bases, or states on arbitrary numbers of qubits. So you can make in both these problems 2 and 3 Imagine the number of qubits is somewhere between 10 and 20. You can again reconstruct these states if the depth of the circuit is not too deep, so that the state is not too highly entangled. So in this problem, we're going to consider this brickwork quantum circuit here, where qubits are only entangled with their nearest neighbors. And in particular, we're only going to consider one layer of this circuit, which is 2 rows of this diagram here. In this case, we're going to generate a random state that has this circuit structure. And again, using a finite number of measurements, you want to find the circuit which inverts this state so that U hidden times your circuit, which generates the state, is as close to your starting all zero state as possible, or equivalently gives you the highest score using the Gibbs score function from problem 1. Now, this is actually quite a bit more challenging than the previous problems, but you should be creative. Try and use whatever methods you can. There's multiple different solutions for problem 3. And if you get a score above 0.5 for most circuits here, you should consider that to be very good. Although it is possible to even get into the 90s for this problem, 0.9 or above. So that's the full challenge. And that should be everything you need. Hopefully you have fun and learn a lot in this challenge. And good luck.